This is my reassessment for Chapter 3. So we are given two thin hollow plastic spheres the size of ping pong, and they have been rubbed together with wool. So they have a charge, and both of them have a charge, and they have a mass of 2 times 10 to the negative 3 kilograms. And we want to know the relative position vector pointing from Q1 to Q2, where Q1 is the first one and Q2 is the second one. We have to use R equals R2 minus R1. So we are given the positions of R2 and R1, and so we just have to plug them into the equation. So R equals negative 30 e to the negative 2, then 40 e to the negative 2, and 0 meters. And you subtract that by R1, which is 30 e to the negative 2, then negative 20 e to the negative 2, 0 meters. And when you subtract them, we will get a vector as well. And the new vector is 30e, let's see, no. R hat minus that. New vector is, and the new vector is negative 0.6.60. Right there. Next, we want to know what is the distance between Q1 and Q2. So we have to find the magnitude of R. And we do that by taking the square root of the vector R of each component squared added together, and we'll get negative 0.6 squared plus 0.6 squared plus 0. And that'll equal the square root of 0.72, which will equal 0.849 meters. Yeah. And now it asks us, what is the unit vector in the direction of R? So to find the unit vector, it's only R divided by the magnitude of R, and that'll give us negative 0.707, 707, and 0. Now we want to know what is the magnitude of the gravitational force exerted on Q2 by Q1. So we use the formula, the negative g times mass 1 times mass 2 divided by the magnitude of R squared, which equals negative 6.7 times 10 to the negative 11 times 2e to the negative 3 squared kilograms divided by 0.849 squared meters. And that'll give us, let's see, 3.718 e to the negative 15. And now it asks us, what is the gravitational force vector exerted on Q2 by Q1? And we use the same formula as before, except we multiply it by our hat. And when we do that, we'll get 2.926 e to the negative 16, negative 2.629 e to the negative 16, and 0. And now it wants to know what is the value of they want to know the value of this. I just can't remember what it's called. Oops. Right there. Okay, And this whole thing be 1 over 4 pi e to the 0, that is 9 e to the 9, it's a constant. And so we multiply that by the Q1 and Q2, and Q1 and Q2 are the charges, and you divide it by the vector r squared, and that'll give you 3.423 e to the 8. And so now, what is the electric force vector exerted by Q2 by Q1? And so here we have the same formula as above, except we multiply by r hat, and we would get negative 2.472 e to the negative 7, and 2.472 e to the negative 7, and then 0 newtons. And the e, remember, is just a short form of saying 10 times 10 to the negative 7. So when you see that e, it's like, say, negative 2.472 times 10 to the negative 7. And so now, what is the ratio of the magnitude of the electrical force to the magnitude of the gravitational force? And we find those two answers up here, and we just have to divide them, and we get 6.423 e to the 8. And now for the last part, if the two masses were 3 times further away, that is, the distance between the masses were 3 times the magnitude of r, what would be the ratio of the magnitude of the electrical force to the magnitude of the gravitational force? And here, I use the same equations as above. All I did was I multiplied the magnitude of r times 3, as you can see right here, times 3. And then I divided it, and I got 9.403 e to the 8. And as you can tell, it didn't change that much from 9.423 to the 8, but it did have a little bit of a change, but not substantially. And so that is my reassessment for Chapter 3.